Welcome everyone to this introductory course in quantum mechanics for computational and quantitative biologists. In the previous lecture, we tried to set up the discussion for our first hands-on experience in quantum mechanics, attempting to solve the problem of understanding the wave function of a particle confined in a one-dimensional infinite well. Here's my particle, and the question that we would like to answer is, what is the probability of finding a particle in a given position in the well? What are the typical energies of the particles in the well? And we began a long discussion, mostly based on physics, in which we were motivating why we use the double well problem, the single well problem, why we use the infinite well approximation, and why do we completely neglect the structure of potential inside a well, and why is this problem relevant at all? And we touched on several issues. And then we attempted to solve the problem from a mathematical point of view, trying to motivate the construction of the solution. Now, while I think that this approach was useful to sort of put things into background and context and try to see how the solution actually emerged, the price to pay for such an argumentative discussion is that of leaving mathematical clarity a little bit behind, and maybe the result is a not particularly clear sequential mathematical derivation. So I decided today to do the opposite approach and look at the problem from a mathematical point of view and trying to resolve the problem, but this time trying to be focusing only on the mathematical aspects. And then maybe at the end draw some physics conclusion. Okay, so what we want to solve, let me remind you that our goal was to solve the Schrödinger stationary Schrödinger equation. For this specific problem. And remember, the problem that we're interested in is one in which the well can be considered constant or zero inside the region between L half and minus L half. And virtually infinite outside this region. Well, like I said the other time, we might want to be a little bit more precise mathematically, and we might say, okay, we don't like to, handle infinities in mathematical derivations. So let's say there's a constant U naught, and U naught is arbitrarily large, which essentially amounts to imagining that there is a finite barrier outside. This is my U naught. But I'm allowed to let this U naught to be as large as I want and draw consequences for that. Okay, so that's what mathematically, how we formulate the problem. Now, the next step we did, and I want to emphasize now, was to say, okay, rather than solving a Schrödinger equation in which the potential has this weird form and take into account of the fact that the potential has a finite shape outside the box, see here, I might as well neglect all of these complicacies and use the effective result of having a large barrier to escape from the box, which is that of suppressing the probability of finding the particle outside the box. So what we said is that rather than dealing with this problem, which is mathematically complicated, we tackled a physically equivalent problem, which was phi of x is different of 0 only for x in the box, or equivalently, phi of x is 0 for x that doesn't belong to the interior of the box. So in other words, we can only find the particle inside the box. So with this in mind, we can neglect altogether this term here, because inside the box the potential is 0, and solve the same free Schrödinger equation we solved for the plane wave problem, remember, but with different boundary conditions. And the boundary conditions are this. The next thing we noticed is that this equation mathematically looked very much like the equation that we saw when we studied the harmonic oscillator problem. Remember, the particle attached to a spring in classical mechanics. The physical interpretation of those solutions and those equations were different from the physical interpretation of the wave function, the Schrödinger equation, but the mathematical structure was very similar. So this was used as an inspiration for looking for solutions. So what we did in the end of the day, motivated by the fact that we're looking for functions whose second derivative is proportional to a negative constant, to the function itself, was to look for solutions in the form of a linear combination of sines and cosines. Now, as you might notice here, I've explicitly from the outset introduced two different constants. In previous lecture, I began with trying to use the same constant, only to notice that if you use the same constant, you cannot satisfy both boundary value conditions at once. So the only way to, satisfy this was to allow for the two constants to be different. And it turns out that if you want to satisfy this constraints altogether, you've gotta, so if k is the index which labels the different eigenvectors, eigensolution of the Schrödinger equations, each solution will come with its own normalization constant and its own parameters, alpha k and beta k. Because remember, we are dealing with an eigenvalue problem. So Evangelic problem means that there is going to be a set of eigenvalues and eigenvectors, which will select some values only for specific value of these a's and alphas and b's and betas. This particular combination will satisfy the equation, Schrödinger equation that I'm writing here, with the right boundary conditions. So we began noticing that we divided the solution in odd and even. And in the end of the day, we discovered that there were odd solutions that were working, and sorry, this is the even solution that we're working, and odd solution that we're working. In particular, let's look at the even solutions. For the even solution to work, we were looking at the second derivative with respect to x squared. We can neglect the overall constant because in the equation it is cancelled. We'll discuss later how to determine this overall constant. So we knew that when you apply second derivative to a cosine, this would become alpha squared k cosine of alpha k x with a negative in front. And therefore, you get the equation alpha squared equal to negative two m e k over h bar square over h bar square. So in other words, the energy associated with this eigenvalue dependent on the specific value of alpha through the equation alpha squared, so 2m alpha k squared, right? That's what this is telling me. Okay, so all I did here was to apply second derivative and multiply by and by the appropriate constant and set it equal to the energy. So what I've done here, once again, just to make sure that everybody is with me on this, I'm applying d squared dx 5k even is equal to e negative of e times 2m h bar squared 5k even. And since this guy is this guy, then you can, erase on the left and the right side the phi k or the cosine. And basically, what you get is an equation relating alpha and this combination, which you write, which I reported here. Okay. Now, this equation apparently doesn't depend on, depends on a free parameter that is alpha k. But then we assume we use the second piece of information we know. In other words, that the wave function must vanish at L half and minus L half. And so from the first of these two conditions, we get an equation setting up, fixing what alpha k is supposed to be, because we know that the cosine should be 0, which means that alpha k times L divided by 2 should be equal to pi half plus minus, and then 3 half pi, 5 half pi's, and so on and so forth, which led to the conclusion that alpha k must be equal to pi over L, 3 pi over L, 5 pi over L, and so on. So as a result of which, we found an entire family of solutions of possible eigenvectors in the following form. So let me summarize all this by saying that we found a family of even solutions, phi k even of x equals ak to be determined. Well, this we will discuss what these constants are, times cosine of. Now, one plus 2k pi divided by there's a 2 here. No, 3, 5L. That was correct. L. Let's see if this equation is actually correct that I wrote here. Yes, it looks correct because when k is equal to 0, so this is my alpha k is equal to pi 1 plus 2k divided by L, and then the energy, corresponding energy, was given by h bar squared divided by 2m, that's alpha k squared. Good. K equals 0, 1, 2, and so on and so forth. We also discussed a family of odd solutions which were obtained in a similar fashion, but this time, these are in the form b of k sine, and in here was beta k x. And now the condition that led to determining what beta is was the fact that sine of L half beta k must be 0, which now implies that beta k is equal to pi one plus k. Let's see. Or if you want, k pi divided by L with k equal 1, 2, 3, right? And therefore, the energy, so here I can write this, beta k is equal to k pi divided by L, and the energy was h bar squared divided by 2m beta k squared with k equal 1, 2, 3. Now, we also looked at the possibility to have a solution in the form of a linear combination of these two. So a linear combination of type alpha even plus beta odd. But we discovered that this can never happen. In other words, anytime alpha k is positive, then beta k must be 0. Sorry, anytime alpha k is non-zero, if a of k is non-zero, then beta k must be 0. And conversely, if beta k is non-zero, then alpha k must be 0. What I'm bringing up with this is the idea that you either have a solution of the first family or you have a solution of the other one, but then a sum of the two will not be a good solution. It will not satisfy the boundary condition altogether. So my family of eigenfunction of the Schrödinger equation are cosine, sine, cosine, sine, cosine, sine. So rather than, if you look at this equation from this point of view, it looks like a very complicated page of equations, possibly generating headache. But things get much more, start to make sense when you start to organize all of these functions in terms of increasing energy. By energy, I mean this parameter here. So if I look at what I've written here, I realize that its lowest energy is actually a cosine, right? So I start for a cosine. So the first energy, which I will call the ground state, will be the cosine solution, h bar square 2m. And if I put simply pi over L. And I guess here is the 2 missing. Yeah, that's making sense. Now it's making sense. Okay, there was a 2 missing there. Fine. So when k equals 0, I get this number, and my solution is a cosine type. When e is equal to 1, the next solution in line will not be the next cosine, because that will have an energy which will be, now rather than 1, I will have 3. 3 squared is 9. However, before I reach the 9 here, there will be a 4 coming from here. So this will be 4 pi squared L squared h bar squared 2m. And the solution will be a sine type. With the corresponding alpha naught is going to be pi over L, and beta 1 is going to be 2 pi over L. And then when I go to the next energy, the next energy in increasing order is going to be again in the cosine family, and it will be 9 pi squared L squared, and this will be in the cosine family. And so far and so forth. So there's many ways you can bookkeeping all of these terms to make sense. But the important thing here to remember is that, well, when I try to draw this on a screen, here's my well. The next term will have a slightly higher energy. So the first observation is that the first energy is not actually 0. And then we come to that. And that's more or less how the first eigenvalue looks like. The second energy, which I'll draw not in black, I'll draw it in blue, is 4 times as large. And the corresponding eigenfunction is sine type. The third energy, which I'll draw here, is 9 times as large. And the corresponding function is going to be a cosine drawn more or less like this. And the more you go up, and you could continue forever building more and more and more and more and more functions and eigenstates from the equations we derived. There are so many things to say about this mathematical derivation. Now, from the mathematical point of view, we completely killed the eigenvalue problem. We are able now to find all the eigenvalues and all the corresponding eigenfunctions, and there are an infinite set, but we have all of them analytic. We don't even have a computer. We can, you want the 100th energy level, I just have to plug and count and all and tell you exactly what kind of function it is and what kind of value of the energy it is. So from the purely mathematical point of view, we have solved the problem. We are able to find all the eigenvalues and all eigenfunctions. But there's, of course, if we are not in a mathematics course here, we are in the physics course. So there's no point in solving mathematics if we cannot extract physics information. And there's so much physics information here that it's even hard how to start. So let me begin by making some observation. And I need to find a way to write my observation. So let me just draw a corner here. And in this corner here, which I will indicate like this, I'm going to write down some things to be notable things about this solutions we have found. The first observation we have is that the ground state energy, the smallest energy you have here, is non-zero. Well, you might say, well, but who cares what the energy is? The energy is defined up to a constant, right? It could as well be zero. No. No, because remember, we already have made a choice. We have set the potential to be zero. So what this A naught means is really the energy minus U naught is E naught. So what we are saying is really that this is a significant value. It's not just something we can set to zero, because if you set E naught to zero, we are setting U naught to minus the potential to minus U naught. So the energy of the particle, the minimal energy that the particle can have in a box with respect to the potential energy is non-zero. So if I were to interpret this classically, I would say the particle can never be at rest. And I put it into inverted commas because the concept of a particle being at rest in a problem like this is in a quantum mechanical problem is somewhat elusive, because we don't have the notion of a particle being somewhere with a given velocity in quantum mechanics. But what I'm trying to say is that the energy is always greater than the potential energy inside. So there is some kinetic energy. So stated differently, particles have kinetic energy. This is very different from the classical situation, where I can let the energy go down as much as I want, and even take the particle rest inside the box. I have solutions with, in classical mechanics, I can give a particle, I can put a particle here and kick it by any finite amount. And depending on how strong I kick my particle, I will give it increasing energy. I can give it arbitrarily small energy or arbitrarily large energy, and anything in between. Because in classical mechanics, I can choose how to kick my particle as much as I want. In quantum mechanics, things go very differently. First of all, there's a minimal energy. My particle cannot be completely at rest. It's highly counterintuitive. But we'll get an explanation for that. Or at least we'll give a name to this in a moment. This fact of having a non-zero lowest possible energy in the system, which only enters in quantum mechanics, this is called zero-point energy. Let's not try to make sense of it at the moment. Let's only keep it there. The second observation, energy is quantized. Because you see, not only the first step, the first energy, allowed energy, is positive, so there is zero-point fluctuation, but you cannot have a particle with this much energy. The only energy that I can have in the system is E. The closest energy I get to E naught is E1, which is 4 times E naught. And the second to next is E2, which is 9 times E naught. Which means that if I were to perform a measurement in my system, measuring the energy of the particle, I will never find a particle, an experiment will never give me an energy, say, like this, or an energy that sits like here. All of my experiments can only return, according to theory, predictions can only return values which is formed of these discrete numbers of energies. That's a strong statement. The system cannot take any energy once, only a few energy. This is energy quantization right there. So the Schrödinger equation that we introduced to describe wave propagation in a double slit appears to be able to describe also a second major feature and property of quantum mechanics. That is the fact that energy can be quantized. So the same equation is accounting for the wave propagation character of quantum mechanical particles and from the energy quantization properties of quantum mechanical systems all together. Let's go forward. Suppose I describe my particle classically. So suppose well, if I know exactly the initial condition, you know exactly where to find the particle at some given time. You know, I tell you exactly at time 0 what kick I'm giving to the particle, what velocity, and where was the particle. Then all you have to do is sort of go back and forth according to straight line. And when I stop the clock, okay, where's going to particle be in 15 minutes? You can stop the clock exactly 15 minutes and find out the only position where you expect the particle to be. And of course, you will make a mistake if you have some uncertainty on the initial condition, but you can make this mistake as small as possible by making better measurements of the initial condition. But now if you have no idea where the particle was at some initial time, or you have no idea what was the kick you gave to the particle, you can only make a statement saying, where do I find the particle on average, right? Because you have no idea where the particle was at some initial time in classical mechanics. And what you would expect in classical mechanics to have an equal probability distribution throughout the box, because the box is flat. The particle can be anywhere in between the two walls with equal probability. That's in classical mechanics, right? So you expect the particle to be, no matter how much the initial energy you gave it, you expect the particle to have the same probability to be found in every point in space inside the box. And clearly, this is very far from what we ended up predicting here in quantum mechanics. Why? Well, let's look at, let's look at the first solution. So let me erase for a moment just to make some space, to make the figure more readable. remember the probability of finding a particle x at time t is nothing but the modulus square of the wave function. Now, suppose the system is in any of these allowed states, say the ground state. So here I will have the ground state, which will mean that I will have e to the negative I over h bar e naught t times my ground state phi naught of x, modulo square. Now this function is real, right? Because it's the cosine. So let me pull it out. Squared. And this is the square modulus of a phase, which means it's the phase times its complex conjugate. The phase will cancel, this will disappear. This is going to be 1. So the probability of finding a particle x at time t will not depend on time. Will be the same for every time. If my particle was in this ground state, right? If it's a ground state at time 0, it will stay in the ground state forever. And the probability will be simply given by the square of this function, which for a cosine is cosine square, or something that looks like this. Now, the probability is not constant through the box, but it's actually small, even vanishing as I get here, which needs to be because my wave function must be 0 here and here, and it has to be continuous. So if I were to look this from above and give a density map, this is my L half and minus L half. Looked from above, looking down, I will get like higher density probability of finding a particle in the middle and lower, 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 lower to that. So most of the time I will find a particle in the middle. Now, what happens if I go to higher and higher excited states? Well, if you look, going from cosine to sine, you get one extra 0 of the wave function. Going from sine to cosine, you get another extra 0. So anytime you rise up in this index that labels the energies, which is called the principal quantum number, n, this will be also the number of nodes in the wave function. What is a node? A node is a point at which the wave function changes sign. For instance, the sine, the cosine has no nodes. The cosine is a function like this and never changes sign. So the ground state has 0 nodes. N equals 0 equals 0 number of nodes. Fine. The sine has 1 node. The first excited state has 1 node. The second excited state has 2 nodes. Now, when I translate this information, the number, the more I go towards higher and higher excited states, the more the wave function starts developing points where it changes sign. When I translate in terms of probability and looking at the probability to find a particle in the case states somewhere in the box here, I will discover that the more I go into higher and higher excited states, the more there will be regions where the probability is 0. For instance, when I'm looking at the sine, the wave function will be 0. The probability will be 0 here. This is phi 1 squared. So it will be 0 in the middle. So, and as I go to the second excited state, it will be 0 here and here because it will be the square of a cosine and so on and so forth. So there will be dark spots. There are regions where the probability of finding a particle is suppressed. with respect to other parts of the box. Now, where these dark spots depends on which is the energy of my particle. If I have a particle with the lowest possible energy, the only region where I'm not going to find a particle are the border of the box. If I have slightly larger, the next to lowest allowed energy, there will be a dark spot in the middle. And if I get next to next, I will get more dark spots distributed around my x-axis. Again, this is an entirely non-classical phenomenon. Right? The more I increase the energy, the more I will be able to locate points. So suppose I know the system for some reason, I have some experimental procedure that determines that my particle will be in one of these states and only one of this. Maybe I prepare the system to be in one of the states that I just told you. I can tell you experimentally which state it is by performing many measurements, look at reconstructing the probability distribution by measuring the position many, many times, and counting the points where I did never expand, how many are the spots in my system where I never observed the particles. Because if the probability becomes 0 in n points, then I will be in the nth energy state. And the nomenclature says that the lowest energy state, E0, is called the ground state, and all the other are so-called excitations or excited states. So in the system, the particle will be found in any of these excited states. I hope you begin to appreciate how distant all this behavior is from a classical behavior. There is something that it's worthwhile noticing. Since my wave function is not infinitely picking a point, the probability of finding a particle in a given position will be always a distribution, right? So I will never be able to tell you the system is at particle X as a position X naught. The particle is actually here or there or there or there. I can only assign a probability to any of these events. So there is the very fact that I'm using wave function carries on uncertainty on position. Interesting. So this is the first step towards realizing that there is a certain probability of finding a particle at a given position, and soon we will discover there is a certain probability of finding a particle with a given momentum. This is not something we have seen so far, but we will see soon. And the uncertainty on position we are talking about comes from the very nature of the wave function. It doesn't come from my incapacity of determining the initial condition experimentally with sufficient accuracy. It's just built into the quantum mechanical formalism. I cannot get rid of it. So there's something intrinsically uncertain in quantum mechanics. And this uncertainty propagates from position to momentum. Maybe we can begin to relate the uncertainties between positions and momentum. So if I cannot determine the position with infinite accuracy, if I have a finite accuracy on position, what is my accuracy on momentum? Well, we can estimate that. Remember, the energy of the ground state was supposed to be h bar square. Sorry. Oh, shoot. The energy, oh, that's wrong. Let's see if we can recover. Yes. It's going to be light. Well, typically the structure I'm getting is of this type, roughly speaking, right? To go back. Now, we know that roughly speaking, this is, I guess, the mass, 1 second, the mass, I guess, was in the denominator, right? Okay, hold on 1 second. Okay, the energy was proportional to h bar squared, high squared, L squared, and S in the denominator. Right, roughly speaking. Then, of course, the number in front of here depends which energy you're looking at. But say for the ground state, maybe there could be factor 1, 4, 9 here. Doesn't matter. Roughly speaking, that's the kind of numbers we get. Okay. But we know that this is typically the momentum divided by 2m, which basically tells me that my momentum is of the order of h bar pi over L. So basically, the uncertainty of my position is of the order of the size of the box, because we have a distribution which is sort of distributed inside a box. So the uncertainty on position is of the level of L. The uncertainty on momentum is of the level of h bar pi to L, which means that roughly speaking, if I multiply the uncertainty on position and the uncertainty of momentum, in this stupid analysis, I get something like this number, which is roughly speaking h bar half. Now, I can never squeeze this minimal uncertainty by performing better experiments. It's something intrinsic in the mathematical descriptions of quantum mechanics. But we know cases in which you can squeeze either x or p indefinitely. For instance, if you have a plane wave, you have a particle which has exactly one particular momentum. Remember, that's the momentum that enters in the phase, p dot x. But the plane wave is infinitely distributed with the same value. The wave function on a plane wave is the same throughout an entire infinite plane, right? In other words, in a plane wave, the wave function is proportional to p to the x. If this is a constant and fixed, You know the momentum exactly of the particle, but this, if this is x, the wave function is the same in all these points of the plane, right? Y and z, so to say. So the wave function is infinitely delocalized in position. So what I'm trying to say is that in quantum mechanics, we found a fundamental limitation that tells me I can never squeeze position and momentum to infinite amount of uncertainty. But if I squeeze the position, I get infinite amount of uncertainty on momentum. In other words, if I know that my particle is in one particular point, I have no idea what is its momentum. We'll see that. It's not completely evident for the discussion we have at this moment. For instance, if I squeeze the walls, then I focus in the position of my particle more and more and more because it has to be inside the walls. But then, since the typical momentum goes proportional to the inverse of the size of the hole, I have no idea what the typical momentum is because it could be anything from 0 to 1 over L times h bar. So by squeezing my information and position, I'm losing information and momentum. Conversely, if I take the wall and I make it larger and larger and larger and larger, my particle becomes a plane wave. At that point, I know exactly what is the momentum of my particle, but it can be delocalized over an infinite amount of space, and so I have no idea where the particle is. This is the fall of determinism in quantum mechanics. So you can see there are so many things that become immediately there by solving this problem, which, although the problem is admittedly a trivial problem in terms of its physics content, there is no real physical system that is well described by a double-world problem. However, so much features of quantum mechanics are already emergent by looking at this problem. And the main point that I want to draw your attention to is that, yes, we were able to summarize a bunch of phenomenology that we had discussed at a qualitative level by looking at the quantization of the energy levels in atoms and the propagation of electrons in a double slit experiment. And the quantum mechanical formulation based on the Schrödinger equation that we devised is actually sufficiently rich in physics to account for both delocalization and energy quantization. The fact that I have a 0-point energy in particular comes from the fact that I have finite uncertainty on position, if you think about this, because the particle can only be in a point from -L½ to L². So my probability of finding a particle is not flat and completely undetermined. The particle can be anywhere. It is anywhere within a region of size L. But then, because of the Eisenberg, or so-called Eisenberg uncertainty principle, which I just wrote here, then I expect also the momentum to have a certain uncertainty. So in particular, I cannot claim the particle is at rest, because if the particle was at rest, then I knew its momentum would be 0. But since I fixed my amount of uncertainty on position, its momentum has to be uncertain. And in fact, if the momentum is certain, you must got a certain amount of kinetic energy. And that's why the lowest value for the ground state kinetic energy is not 0, it's finite. See, magically, all these features that look so counterintuitive are simultaneously captured by the mathematical description of the Schrödinger equation we are setting in place in this lecture. So, I'd like to leave this lecture with a loose end, because there is one more point we will dedicate one more lecture to discuss. And the point being how do I understand classical mechanics from quantum mechanics? I mean, on the one hand, we understood that if I take a classical particle, sorry, quantum mechanical particle, I think, we might be more or less confused, but we sort of got the point that we have to use the Schrödinger equation, we have to use the wave function, and then if you follow the mathematics, you come up with these results that we just listed here. On the other hand, we know that if the particle is a macroscopic particle, well, it behaves entirely differently. How did we go from the quantum particle to the real particle? How do we understand the transition? Because all I mentioned here is the Schrödinger equation, and one of the features that quantum mechanics should have is that if you, in the appropriate limit, it should contain classical mechanics, because we know classical mechanics is right, so it cannot give predictions that are always wrong, always different from classical mechanics. Otherwise, we would see quantum mechanics in the macroscopic world, and we do not see quantum mechanics in the macroscopic world. So something must happen inside the theory such that as I change the parameters and I get the system settings more similar to that of a macroscopic system, all these magic features that we discovered happening in the quantum mechanical world sort of disappear, and I get back the classical, boring, trivial predictions that I knew from classical mechanics. This kind of correspondence between quantum mechanics and classical mechanics, so the statement that classical mechanics should be contained as a special limit of quantum mechanics, is called the correspondence principle. And we want quantum mechanics to obey the correspondence principle. And in the next lecture, we will discuss this relationship in detail, applying it again to this problem and trying to see whether from this problem we can recover the correspondence principle and the classical behavior that we expect. Okay, thank you very much. I think I'm done. Take care.